Hello and welcome to another class of ATMO 620. I hope you're all doing well. I hope you're enjoying the class so far and that the material was clear last class. Just as a reminder, we had a bit of a change of pace from when we were just talking about microphysics, and now we are immersing ourselves in this beautiful topic, which is the interaction between radiation and the atmosphere. Radiation is kind of a dark horse, and we don't. I think not many of us aren't probably very familiar with the radiation, and so I think it's good to go over the bases and kind of introduce the basic material before we get deeper into the topic. What I want to talk to you today about is an interesting subject, which is molecular spectra. Okay, we saw spectra a little bit last time. Today we will talk a little bit more about spectra and how they interact with radiation. So let's start with a very simple state and a very simple system. Consider a very simple case where you have two masses, two different masses. You could think of them as two different molecules, or whatever. They have two masses, m1 and m2. m1 different than m2, and let's say they're separated by a distance x. Okay. In the case of molecules, that would be empty space. But you could think, if we wanted to think about sort of a more classical system, you could connect them by a spring, okay? And if you connect them with a spring, then there's a law that dates back to Hooke's, from, if I'm not mistaken, the 17th century. Hooke's law tells us that these two masses are, what am I going to say? That the spring exerts a force on the masses that is proportional to the displacement. Okay, so suppose you have this spring, and let's suppose that the spring is at rest. If in a classical system you have these two masses, and there's a spring in between. The spring is at rest initially. You perturb the first one a little bit. Let's suppose we're in empty space. These two will begin to oscillate and to vibrate. Okay. Quantum mechanically, something very similar happens. Okay. That's why it's important to kind of idealize this. And you could compute if indeed there was this spring, and you assume that the spring obeys the spring law, or the laws of springs, that the force between these two is proportional to the displacement, and k is a constant there that is characteristic of the speed of the spring. Then with classical mechanics, you can show that the frequency with which these two weights oscillate is inversely proportional to the square root of this object called reduced mass. Okay, and what this is something that obeys this law. Okay, and proportional to the square root of k of the spring. Notice once again we have our good old friend pi that shows up here. But so you have this oscillation, and there's a way to characterize this oscillation. Well, quantum mechanically, things are a lot more complicated. I mean, they're kind of similar, but they're also kind of not. And in quantum mechanics, we talk about, we can think about a similar system where you have these two weights kind of connected by something that looks like a spring. Okay, and this in quantum mechanics, or in physics, is known as a harmonic oscillator. Why is it called harmonic oscillator? We don't need to get too deep into this, but that's sort of the technical term. Well, if you remember, in Planck's results, we saw that the energy of the photons were kind of discrete. We saw that the orbitals in the hydrogen atom were quantized, and only certain orbitals were possible, meaning that the hydrogen atom can only exist in certain energy states. So you could think that something similar applies to other cases, this kind of a discreteness, if you will. And indeed, something similar happens here. And it turns out that if you have an oscillator like this one, then this oscillator can only have a finite amount of, not a finite amount, pardon me, sort of a particular set of energy levels, okay? So it doesn't have like a continuum of energies, but it can only occupy certain energy levels. Okay. How do you compute those energy levels? That's kind of technical, and we don't need to get into that. If you're curious, this is kind of how you compute that. This is known as the Schrödinger's equation, and it's the equation that changed everything in quantum mechanics, right? And yes, Schrödinger is the same guy as the cat. As the Schrödinger's cat. And if you solve this equation, you'd find that the energy, this quantity here, can only be, is proportional. Energy is proportional to n, where n is a natural number, a positive integer. In particular, this is what the energy levels look like. Here I wrote n, but we can use w, as I did here, just for consistency. So the energy levels in the system where you have these two springs are given by Planck's constant, again, nu0, which is some kind of a fundamental frequency, much like we saw here, some kind of fundamental frequency of the system, but also different numbers. In particular, notice that these numbers are half integers. W is an integer number, and 1/2 is, well, 1/2, right? And so this W can go from 0 to infinity, and so the energy levels would be h nu0 times 1/2, h nu0 times 3/2, h nu0 times 5/2, and so forth. Okay, these are the energy levels of this system where you have the two molecules kind of attracting each other. This W here is known as the vibrational quantum number. And what I'm showing here are exactly the different energy levels. We don't need to worry about why there's a parabola here, but these are the different energy levels, and these curves represent what in quantum mechanics is known as the wave function. Again, don't need to remember that. Remember that if you have two things that are kind of attracting each other like an oscillator, then this system can only have a finite amount of, a discrete set of energies, pardon me. The amount is infinite because W can go all the way to infinity. There's no limit. But it can only go with these discrete jumps. How do you go from h nu0 times 1/2? How you go from this energy level to h nu0 over 3/2? Well, you guessed it, by absorbing a photon. What energy does the photon have to have? The photon has to have energy h nu0. How do you go from h nu0 back 3/2 to h nu0 times 1/2? You guessed it again, you're emitting a photon. What energy does the photon have? Energy h nu0. Okay, this is kind of how it works in quantum mechanics. Okay. Now, it's interesting because the absorption of a photon is made possible by a coupling between the electric field and what we call a dipole moment. Yeah, an electric dipole of the molecule. An electric dipole is something that happens whenever you have two charges, right? Two charges like this, negative and positive. The electric dipole is a vector that is proportional to the charge and goes in the direction of this sort of charge gradient, if you will. Okay. And interestingly, this electric dipole exists for molecule where there is a net separation of the charges. So in some molecules, like water, this kind of looks like Mickey Mouse, but this is a water molecule. Right? You have oxygen and you have hydrogen. Now, oxygen is a very, very greedy molecule, okay? And therefore, it tends to kind of attract all the charge, okay? The electrons, they're much happier to spend time here than they are to spend time here. So these two nuclei, which are a proton, and a neutron, but these nuclei have a positive charge. These two electrons here make this system negatively charged, right? Because this has enough charge to neutralize its own electrons. But if you add two negative charges here, you tend to have negative charge. And so if you were to look from really far, this molecule, you would have an excess of charge on top and a positive charge on top and an excess of charge near the bottom. Okay, and so when you have very asymmetrical molecules, it's easy to have this dipole, and so you can very easily have these kinds of absorptions or emissions. But if you have linear molecules like oxygen or nitrogen, these tend to have a symmetrical charge distribution, and therefore their electric dipole moment is zero. Okay, meaning that these absorptions or emissions cannot happen for them. Okay. And so one of the consequences of the fact that the coupling happens through the dipole moment is that the emission or the absorption of a photon, which if you will, it's a bit like an exchange between the molecule and the electric field, has to be accompanied by a change in the dipole moment. Okay. And we don't want to get into the details, but in quantum mechanics, you can only change the dipole moment by so much in one go. Okay, and in particular, in this particular case of the harmonic oscillator, if you have two molecules that are vibrating like an harmonic oscillator, and they want to absorb some radiation, and they want to go from the state h nu over 2 to h nu 7 over 2, then this cannot happen. Okay, there's a rule in quantum mechanics called selection rule that says that this cannot happen. If this molecule wants to go all the way to this energy state, it has to go first from h nu over 2 to h nu 3 over 2, and then h nu 5 over 2, and then h nu 7 over 2, then finally here. Okay, sudden jumps cannot happen, like between multiple levels. You can only go from one level to the next one. If you're interested, the reason why that is that, well, photons are also associated with something like an electric dipole moment. And if you're absorbing a photon, you can only flip by how much you're absorbing or emitting through the photon, right? If you are changing your state and you're either absorbing or emitting one photon, because the photon is associated with one flip of the dipole, the electric dipole moment, you cannot have more than one jump. You could think about it that way. So there are, by this rule, there are some transitions between energy states that are allowed, as we say, some that are forbidden. Okay. A forbidden transition is kind of a misnomer in the sense that they're not really forbidden. Nothing is forbidden in quantum mechanics. They're just extremely rare, extremely unlikely. Okay. One example where you could actually see these kinds of selection rules in action is with fluorescent material. Fluorescent materials are created by bringing the material in a particular configuration, if you will, and then sort of in kind of an excited state, and forcing the material in that state, and the material is in that state and has no ways of going back to the bottom stage, to the ground state, if you will, because what would take the material back to the ground state is a forbidden transition. However, because these transitions are not strictly speaking forbidden, but they're a lot more rare, they happen more rarely, but they still happen. And when you see the fluorescent material fluorescing, you're observing these transitions that happen slowly, one after the other, right? If all the transitions were made possible, right, if there was no selection rules, during the day when the fluorescent material absorbs solar radiation or whatever, it becomes excited. And at night, when it wants to go back to the ground state, if there was no selection rule, then it would go back to the ground state in a nanosecond, like you wouldn't see it. But because these rules are extremely rare, there's one every, I don't know how long, but longer than a nanosecond. By the time all the transitions have happened, the night has passed or something like that. Fluorescent materials don't last forever, and that's the reason why. Because at some point, all the atoms or molecules that make up the fluorescent material are now back to the ground state. Okay. Okay, so vibrational state, that was kind of easy, and we kind of knew what was going on. So we saw there are vibrational states and selection rules associated with vibrational states. You cannot jump more than one vibrational state at a time. Okay. If you're a little confused about the electric dipole moment, if you're not familiar with the concept, don't worry. Just remember you can't jump more than one. Okay, so the orbitals are quantized, the vibrational states are quantized. What about the fact that molecules, like complicated molecules like, N2 molecule, N, what about the fact that this molecule can rotate? Do you think that this rotation would also be quantized? Well, yes, you guessed right. If you want to know the whole truth, this is part of the ways to determine that these are quantized. Again, we don't need to get through this. The bottom line is that, so feel free to ignore this. If you don't know what a free Hamiltonian is, spherical coordinates, don't worry. Spherical harmonics, feel free to ignore this. But the important thing that you have to keep in mind is that the possible rotational energy, the possible rotational states that are allowed by quantum mechanics have, again, very definite energies. And these energies are proportional to, first of all, this is something similar to the Planck's constant. Whenever you have the cut sometimes you see H, sometimes you see H cut. Like this, H cut is nothing but H over 2 pi. And the reason for doing this is that very often, for whatever reason, there's always a 2 pi, and in order to be a little bit cheap, people say, let's just write H bar, H cut. It's not actually an H bar, it's really just an H cut. So it's proportional to the square of Planck's constant divided by the moment of inertia of the molecule, okay? times this factor here, j times j plus 1, where j now is an integer number, 0, 1, 2, etc. So the ground state, in this case, has Ej equal to 0, meaning that you're not, this molecule is not rotating. And this is in stark contrast with this, in this case, where W equals 0, you still had some energy. So even when you're at the very, very ground state, your oscillator is vibrating. Why is that? Well, we don't want to get into that. But vibration E can never be 0, rotation E can be 0, and that's okay. And that's how they grow, okay? So you go, these numbers are 0, 2, right? 1 plus 2. 2 times 3 is 6. 3 times 4 is 12. Gosh, it's embarrassing. I can't do math anymore. And so forth. Okay, so again, discrete rotational states, discrete vibrational states. The reason, so important thing. Vibrational states, well, rotational states are degenerate, which seems like a bad quality, but in quantum mechanics, it's okay. It doesn't have the attributes that we humans give it. Degenerate means that there can be different physical configurations corresponding to the same energy levels. Okay? Vibrational states are not degenerate. One vibrational state, it has to have that particular configuration. For rotational states, that's not quite true, and they can have different configurations. Okay? Now, we had selection rules for vibrational states. Do you think we'll have selection rules for rotational states? Of course we have. And they're exactly the same. So you can jump from one state to the one close to it, but you can't jump more than one. These are some examples I just wanted to show you of what vibrational states might look like. Rotational states are kind of simple to think about, right? I mean, if you have something like CO2, where you have C in the middle and 2 oxygen atoms, this can rotate in the horizontal, it can rotate in this direction, it can rotate in this direction. So this is kind of simple. But the vibrational modes are more complicated. And in this case, you can have a configuration where you can have different kinds of vibrations that are associated with different kind of vibrational modes. And so one mode has the oxygen atoms vibrating in this direction. One has the oxygen atoms vibrating in this direction while carbon vibrates in this direction, or more complicated things. H2O is different and has different vibrational modes because the molecules are at an angle. This is about, this angle is about, I'm quoting by memory, it should be around 106 degrees, right? And so while this is 180, this is 106, and so it has different ways to vibrate. Also the molecules, the atoms have different atomic masses. And so you could imagine that when you have a molecule, when you have a gas of molecules, this gas is absorbing it's always absorbing a lot of photons and emitting a lot of photons. There's a lot of transitions going on. And so you could imagine the spectrum of a gas of molecules being very complicated and much more complicated, much more complex than the spectrum of the hydrogen atom. Like we saw for visible radiation, for the visible part of the spectrum, we saw that the hydrogen atom had lines that looked like this, that were kind of spaced out like this. But for molecules, now you can have vibrational states and rotational states as well, right? And so you'd expect a lot of lines if this was a molecule, right? These are all the different lines. Sorry, I kind of botched this. But anyway, vibrational states have wavelengths that range from 1 to 20 micrometers, so they're typically in the thermal infrared. Rotational states are less energetic, and they are in the far infrared. Okay. Rotational states, therefore, have less energy than the vibrational ones. Okay. And so you could imagine that when you have, when you have a vibrational state, you could imagine that here you would also have, let's say that you're looking at let's say that you're looking at a particular part of a spectrum where you have a rotational wave, you have a very complicated molecule, and here you know that you have a line that corresponds to a rotational state. Typically, you also have, to a particular vibrational state. Here, you typically also have a lot of other lines that correspond to the same vibrational state, but also different rotational states. Okay? I hope this is clear. All the different emissions can happen at the same time, right? And so it could be that you're jumping maybe from a lower level and you're jumping to lower vibrational level, you're jumping to this vibrational level, but with different rotational energy. And so that's why sometimes when you look at spectra, the spectra have sometimes, they have a major peak, but they also have, along with this major peak, they have a lot of smaller peaks nearby. A transition from one peak to another is like going from one vibrational state to another, but these correspond to different rotational states associated to that vibrational state. I hope this is kind of clear, but it's just to say that's why sometimes spectra are confusing and they have a complicated shape like that. All right, so we talked about the electric moment. Have you ever noticed that when we talk about greenhouse gases, it's always like CO2, methane, which is CH4, water vapor, which is H2O, but you never hear people say that nitrogen, N2, it's a molecule with a bond, or so N2, or oxygen, which is kind of similar. You never hear people say, well, oxygen and nitrogen are greenhouse gases. Well, that's because they're not. And one of the reasons why they're not is that they are very symmetric. And because of their symmetry, they do not have an electric dipole moment. And so they interact very weakly with radiation. They interact very weakly with thermal radiation, which thermal radiation is usually in sort of the spectral window that excites rotations and vibrations. But because of the symmetry of these molecules, photons in the thermal infrared or far infrared cannot be absorbed by these molecules. On the other hand, these molecules have the right shapes and the right asymmetry to absorb these molecules, and that's why CO2 and H2O are better greenhouse gases than nitrogen or oxygen, or like dry air, if you will. Okay, and this looks kind of messy, but this is just to say that there are also other kinds of transitions, other kinds of molecular transitions other than vibrational and rotational. And these transitions are so-called electronic transitions. Now, remember that I said, well, I don't like the word orbit. I prefer orbital. The reason why that is that before I showed you a picture like this one, right, where you had two hydrogen atoms and two oxygen atoms. And here you could see that there are very definite orbits. Hydrogen is a circular orbit, and oxygen is very circular orbits. Nature is a lot more complicated. And what typically happens is, if you were to zoom in, this is exactly a water molecule, is that each atom has its own orbitals, and these are described by quantum mechanics, and they're kind of well definite. But when atoms become close together, their orbitals kind of merge in a way, okay? And they acquire a lot more complicated shapes. And associated with different kind of orbitals are different kinds of energies and also different kinds of positions of electrons within these orbitals. And so this is an example of all the possible orbitals that a water molecule can have. These colors, you could think of them as a probability of finding an electron, okay? So the ground state is this one, just kind of basic, if you will. And then you go to more excited states, and notice how exotic these are, you know. These are higher energy levels. And so when you're hitting an atom like water, you're hitting it with a photon. You could certainly make it rotate, you could make it vibrate, but also you could make one of the electrons in this molecule jump to a different orbital, okay? And actually, you could even ionize this molecule. Like you could provide enough energy to this electron that the electron would just, boom, leave the molecule altogether, okay? And the electron would take all the energy that was needed to break free from the molecule, and the additional energy that it took from the photon, it will convert it to kinetic energy and, you know, become really, really fast, right? Electronic transitions typically require a lot more energetic radiation. So ultraviolet, visible photons, these can make electronic transitions happen, okay? Which much, much smaller wavelengths than rotational and vibrational energy. This is an example of the transitions that can happen. This is, imagine, let's think about this system here. The curve I'm showing here is the energy. Let's suppose that you have two molecules, A and B, okay? And these, two atoms, A and B, and these make a molecule. Let's suppose that these A and B are at a certain distance d, okay? And this configuration has an energy associated with it. The energy as a function of distance between these two molecules is this function here, okay? Now, this system has discrete energy levels up to a certain point. But past a certain point, so when you reach a certain energy, the energy spectrum is not discrete anymore. And so what could happen? Well, a few things could happen. It could happen that you're in this state, you absorb a photon, and you go to a slightly more excited state. And that's okay. You know, maybe you're going from one vibrational state to another, or from one rotational state to another, okay? Or you could absorb, for example, you could absorb what am I thinking about? You could absorb a photon and you break this bond. And so this is what we call photodissociation, okay? So the molecule has been broken by light. Or it could happen that you absorb a photon and boom, you jump to another state that is a bound state, but where one of the atoms is in an excited state. Finally, you could absorb a photon that dissociates this molecule, so break A and B apart, and sends one of the atoms to an excited state. Okay. These are all examples of transitions that could happen. Okay, so just as a small recap, we talked about photons and molecules, just to recap on what could happen. In terms of the interaction between photon and molecule, that could be something that we call scattering. Radiation, a photon is temporarily absorbed by a molecule or an atom, and then it's re-emitted. And this is what in classical physics we would call diffraction, refraction, reflection, and that kind of stuff. In the small scale, this is just scattering. Or we could have absorption, and the absorption is kind of permanent in this way of thinking. When you absorb a photon, the photon doesn't exist anymore. It's become energy, okay? And this absorption could lead to photodissociation, okay? This requires a lot of energy. Could have an electronic transition. This kind of requires a bit of energy. And you could have vibrational transitions. You could have rotational transitions at lower energies. But also remember, there are forbidden transitions. So not all transitions are allowed. Okay. In terms of absorptions, in the atmosphere, we're somewhat lucky to have some gases that are doing a really good job at absorbing stuff. First of all, I think about oxygen, and well, oxygen is a great gas. It's kind of toxic, and so you die if you breathe too much of it. But we're lucky that in the atmosphere close to the surface, there's about 22% of oxygen, and so it's okay. But oxygen is present in the atmosphere in two forms. A molecule with two oxygen atoms, and a much rarer, if that's even a word, a much more rare form of oxygen that is made of three oxygen atoms. This is what we call ozone. This is a lot higher in the atmosphere, all the way up in the stratosphere. This is important because oxygen and ozone absorb in the ultraviolet spectrum. This is great because the sun also emits a fair amount of ultraviolet radiation that would kill us otherwise. Methane, CH4, CO2, and H2O are also great absorbers, but they absorb in different spectral range than oxygen. They absorb in the infrared, okay? And in particular, they are important in the infrared, and that's what makes them greenhouse gases, because the Earth is emitting infrared radiation to space, and these gases essentially get in the way of the infrared radiation that is trying to go to space. And some scattering happens, and so some of that radiation is sent back towards the surface, and that's, in a nutshell, that's the greenhouse effect. I mean, there. In a few words, that's what the greenhouse effect is. This is an example of the absorption spectrum of the atmosphere. So it's similar to, if you remember last lecture, I showed you this curve here. And there was a red curve below that was similar, but not quite exactly the same. Well, if you took this thing and you divided by the Planck's function, you obtain something like this. So transmittance is what would pass through if nothing was absorbed, okay? So the sun is emitting with some spectral power like this. If there was no atmosphere, this is what we would be receiving on the surface. But because there's the atmosphere, some of it is absorbed. And so what we observe, what we see at the surface, is something that looks more like this, right? And so divide this by this, and you get exactly this. And all this stuff is missing because of the gases that are in the atmosphere. This is as a function of wavelength, so small wavelength, this is high energy. This is deadly stuff, ultraviolet radiation. Thank you, oxygen. Thank you, ozone. Very little gets transmitted through. And then here we have something that is absorbed. Here it's all gone, and this is all due to water vapor that absorbs in this part of the spectrum. And yeah, some of these absorption regions are kind of well known, and if you go on the webpage of GOES 17 or GOES 15 satellites, sometimes you can observe, it shows you that you can observe different water vapor using different channels. And the different channels are something like 11.2 micrometers and stuff like that. Well, those channels are exactly this. You're observing the radiation that is emitted by water vapor at that precise wavelength. This, we'll get back to this, but this is another way to, let's just focus on this. This is another way to visualize. So this is the spectrum here is what I showed you here. And this is a way to break this down in different gases, okay? So this is the role of carbon monoxide. This is the role of methane, N2O, ozone, CO2, HDO, H2O, and this is the sum. So, you know, for example, when you look at the solar spectrum and you say, oh, you know, here there's a dip. What is this due to? You can go back and say, okay, yeah, this is due to ozone. What about this guy? Well, this is almost entirely H2O, and so forth, okay? Last thing that I wanted to talk to you about today. Now, if what I said to you so far was exactly true, so remember Niels Bohr atomic model, that atoms had to have exactly, that photons had to have exactly the same, a very specific wavelength when they're emitted, then when you look at absorption spectra, right, when you look at a spectrum, the spectral lines that you see would be so thin, they would have to be so thin that it would basically be impossible to see them. So why do we see them? Okay, and the reason why we see them is due to a variety of effects. Okay, this is what we call spectral broadening, if you will. Okay, this is an example. I kind of like to watch these pictures because, well, I guess they somehow atomic visible spectra remind me of, you know, sort of the 1980s aesthetics with like neon lights and stuff. But anyway, you know, it's somewhere between 2001, A Space Odyssey, and Blade Runner. But anyway, this is the light that is emitted by a mercury lamp. And mercury lamps, obviously being lamps, emit a light, shine that through a prism. These are the colors that you get. Same sodium. There's also sodium lights, the ones that are kind of more yellowish when you see. This is what they look like. But fun fact, if you put sodium under an insane amount of pressure, this is the spectrum that you observe. Okay, so here you see there's a kind of line, but notice that when you have a lot of pressure, now this line has kind of leaked out, and same for this, and also this is kind of leaked out, which is kind of bizarre. So why is it like that? Why is there spectral broadening? Well, this is due to essentially three factors. The first factor is what we call natural broadening. Natural broadening is a consequence of quantum mechanics, okay? And I don't know, you're probably familiar with the so-called Heisenberg's uncertainty principle. The uncertainty principle says that you cannot observe the position and the velocity of a particle with exact precision at the same time. So if you call the error that you're going to make in measuring the position, you call it delta x, and the error in measuring the particle's momentum, delta p, then Heisenberg's principle says that the product of these two uncertainties is always going to be greater than h cut over 2. Always. There's a different formulation of the Heisenberg's uncertainty principle, where position and momentum can be substituted with energy and time. And applied to our particular case, this is to say that we cannot measure the time, the duration. What can I say? The lifetime of a particular state and the energy of that state with exact precision. So imagine this molecule, okay? This molecule absorbs a photon, and then after a while, this goes from a ground state to an excited state, and then after a while, it emits the photon back. So there's a certain time where this molecule is excited, and this jump in energy, okay, multiplied by this is always going to be greater than h cut over 2, meaning that delta E is always going to be greater than 0. And so you cannot, the spectral energy, the energy cannot be known with perfect precision. So there's always going to be a little bit of uncertainty, okay? And this broadening is represented by a so-called Lorentz distribution function, okay? This is often a neglected effect because it's minor compared to other effects that happen. The other thing that happened is that, it's called pressure broadening or collisional broadening, is the fact that gases are made of many molecules, and molecules can undergo collisions while they are absorbing or emitting photons. So imagine this molecule here. It's emitting a photon, and in the process of emitting the photon, it gets hit by another molecule. And this process is kind of truncated, if you will, or it kind of interferes with the emission of the molecule, and that kind of messes with the energy and therefore the frequency that is emitted. And you can show that the spectral line, because of this broadening, so instead of being just a sharp stick, the spectral line has more of a curve aspect, So if you were to look at the line, it would be super bright here and then dim, it become dimmer and dimmer as you move out, This can be described with this function, which is a Lorentz distribution. And nu n is the frequency of that state. Nu is your variable, right? You're moving through the spectrum. And gamma L is a parameter that can be computed, and it's estimated to be proportional to the pressure that the gas is experiencing and inversely proportional to the square root of the temperature of that gas. There's also another thing that is the Doppler broadening. Now, you may be familiar with the Doppler effect from sound waves. A wave that is approaching you or that is moving away from you is perceived with a different frequency than you would perceive it if the wave emitter was at rest. You hear ambulances approaching or whatnot. They have a different sound that they had if you're standing on the ambulance. Something similar happens for electromagnetic waves, okay? And in particular, if you have an electromagnetic wave that is emitted with frequency nu0, and the emitter is moving at velocity u, either towards or away from you, then the frequency with which you would see that is nu0 times 1 plus or minus u over c. This happens in everyday life. So, if someone is driving towards you, you will see it with a different light than you would if they were not driving towards you. Particularly if, let's suppose that you're here, if something is driving away from you, like let's say that something is emitting wave, if it's driving away from you, you'd see it with a longer wavelength, but if it's driving towards you, you'd see it with a shorter wavelength. And so if something is coming towards you, you'd see it bluer than it actually was. If it was driving away from you, you'd see it more red than it actually is. Why have you ever noticed this? Well, because the denominator here, this is the speed of light, which I'm sure you will remember is 299,792,458 times 6, I think, meters per second, more or less, which is a lot. And so it's unlikely that your car will ever approach this speed. But molecules do approach the speed. If you heat a gas high enough, the molecules, you have the tools now to compute the speed of molecules in a gas, and you can show that it becomes kind of an appreciable effect. And in particular, remember the Maxwell-Boltzmann distribution, where molecules in a gas had, the velocities of the molecules had some kind of a distribution. So some molecules have a very, very high speed, and they're moving away from you at great speed, and some of you are coming towards you at great speed. Okay? And so this also contributes to broadening. And you can show that this has not quite a Lorentz distribution, but it's more like just a Gaussian shape, and you can estimate the broadening factor here as something that looks similar to things that we've seen before. And finally, the truth is that both of these kind of happen in the atmosphere. And so in some cases, one is maybe dominant, between 20 and 50 kilometers. Collision and Doppler broadening are at play, are important. And therefore, because both are kind of important, the final distribution, the final shape of the absorption or the emission line for atmospheric gases is a combination of the two, okay? And we call those void profiles, okay? So that explains why we don't observe, sharp lines, but there's always some kind of a natural broadening. Okay, this concludes all I had to say about molecules. And as usual, let me know if you have any questions. If some things were not clear, feel free to get in touch, and I'll be more than happy to explain any of the things that were not clear. Otherwise, thank you for listening, and I'll see you for our next class.